Hey guys, today we're going to start our next unit, which is, there's a big, an energy unit. So we're going to start with our concept one, nature of energy. You don't have the note packet for this, so you're just going to take notes on a separate piece of paper, please. And then hopefully when I see you again, we will already have these all done and we can keep moving on. So energy is the ability to cause change. So you can almost think of like if you're laying in bed and you're super tired and you're like, I have no energy to get up. You're not getting up because you don't have the ability to cause change. You don't have that extra energy. And we measure it in joules, which is a capital J, always a capital J. And that is named after a scientist who helped really discover how we can measure energy. And 1 joule is equal to 1 kilogram meter squared per second squared. You won't really need to know that. You'll need to have it written down. You can always write joule, but that just is telling us that all of our other pieces of our equations are going to need to be in kilograms and meters and seconds. There's a ton of different types of energy. You guys saw some of them talked about when we were looking at the Science of NFL videos, but we're just going to start with talking about kinetic and potential energy, and then we'll move on from there in the next concept. So kinetic energy, we represent it with Ke, and that's just saying that it's energy in motion. So something is moving and it has energy and it's taking that energy on with it. And the equation is that our kinetic energy equals 1/2 our mass times our velocity squared. So your mass is measured in kilograms and your velocity is measured in meters per second, again, so we can come back and like have those joules be right. So let's do example number 1 here. A jogger with a mass of 60 kilograms is moving at a speed of 3 meters per second. We want to know what his kinetic energy is. So we're going to write down what the question is telling us. So we're trying to find our kinetic energy. Our mass is 60 kilograms and our velocity is 3 meters per second. So we're going to use our equation, Ke equals 1/2 mv squared. And we're going to fill in our numbers. So our kinetic energy is 1/2. In your calculator, it's easiest to just type 0.5 times 60 times 3 squared. Now, if you're not sure if your calculator is going to read your mind the right way, you can always start with squaring the 3 first and then multiplying everything together, because you don't want it to accidentally square everything or square parts of it and do some weird stuff there. So this is the same thing as saying that 30, so 1/2 times 60 times 9, which is our 3 squared. So our kinetic energy is 270 joules of energy in that jogger. So for practice, we have a baseball with a mass of 0.15 kilograms, and it's moving at a speed of 40 meters per second. What is the baseball's kinetic energy? Let me go ahead and get my other screen pulled up here. I think that's recording. Shoot, I don't know if that's recording. Okay, well, we'll just keep going. So we have a baseball with a mass of 0.15 kilograms and it's moving at a speed of 40 meters per second. What is its kinetic energy? So I know that my mass is 0.15 kilograms and my velocity is 40 meters per second. What is its kinetic energy? So I'm going to use my kinetic energy equation, which is 1/2 mv squared, and I'm going to plug those numbers in. So Ke equals 1/2 times 0.15 times 40 squared. So when I plug that into my calculator, 0.5 times 0.15 times 40 squared, I get 120 joules of energy. For number 2, the stone has 390 joules of energy. So my kinetic energy is 390 joules, and it's moving with a speed of 12 meters per second. What is the mass of the stone? So my equation is Ke equals 1/2 mv squared. And I'm trying to get mass by itself. So I'm trying to move everything else over. And because it's all multiplied, I can divide by my 1/2 v squared on both sides. So I'm just canceling both of those sides out. I'm going to get that my mass equals my kinetic energy divided by 1/2 of my speed squared. So when I plug in my numbers, that's going to say 390 divided by, and I'm going to do 0.5. It's the exact same thing. And then 12 squared. So I type that in, 390 divided by my parentheses, 0.5 times 12 squared. So I'm going to get, and please try typing these in your calculator along with me because there's a lot of little things that can happen. So I want to make sure that you're getting the same answers I'm getting on your end. So it's going to be 5.42 and it's mass, so we're going to have it in kilograms. So what's the velocity of a 0.06 kilogram ball moving with 75 joules of energy? So my mass is 0.06 kilograms, and my kinetic energy is 75 joules. So I'm going to use my equation. And I'm going to go ahead and move everything around to get my velocity by itself. So same thing I did before. I can divide by everything that's not velocity. It's 1/2 mass, 1/2 mass. That still leaves me with velocity squared. So what I have to do is take the square root of my kinetic energy divided by my 1/2 times my mass. Go ahead and put those in separate. And that's going to give me what my velocity is. So this one gets a little bit more complicated. So I'm going to plug in all my numbers. So 75 divided by my 0.5 times 0.06. So I'm going to do this in steps. I'm going to go ahead and multiply my bottom. So 0.5 times 0.06 should give me 0.03, and it does. So 0.03, and then I've got 75 on top. So now I'm going to do this inside part. So 75 divided by 0.03, and that's going to give me 2,500. Then I'm going to square root 2,500. And my velocity, I ran out of space, is 50 meters per second. That one got a little extra complicated there for just a second. Let me pull back up. Okay. So moving on now. Look at that. All right. Our potential energy. So our potential energy is stored energy. It's the potential that you could do something. Like you got energy there, you just got to use it. So there's 3 types of it. There's elastic potential energy, chemical potential energy, and gravitational potential energy. So we're going to go through those. Elastic potential energy is energy that's stored in objects that are being compressed or stretched. So if you have a spring, like in almost like your mechanical pencils and pens, and you compress it, that spring wants to stretch back out, but it's just sitting there stuck that way. So it has energy that it wants to go back out with. So that's potential elastic energy. Or if you're stretching a rubber band, you know that if you let go, it's going to change and it's going to snap something. So that is our elastic potential energy. So the examples they have are like a bow and arrow, a spring, or even a slingshot. If you pull a slingshot back or an arrow back and a bow and arrow before you release it, we have elastic potential energy. The chemical potential energy is energy that's stored in chemical bonds of different compounds. So we'll talk about all the chemical stuff later in second semester. But every chemical has the ability to react. So there's energy stored in it somewhere. So an example like firewood. When you light firewood on fire, you're breaking chemical bonds that are allowing it to release that potential chemical energy and it becomes heat. Or a battery. Battery is just a whole bunch of little chemical reactions that are happening together to provide energy to your electronics and even food. So you can find chemical potential energy in any food because food provides you with the energy to complete different tasks. It gives your body energy. Whether it's all good energy depends on the food you're eating. Then potential energy for gravitational. There's no good place to move my face. There we go. So gravitational potential energy is like our Newton's cradle, and it's when we are above the Earth's surface and we're just waiting there. Energy is stored. If we were to stop holding it, we would be using the energy, but we're just waiting. So you're standing on a cliff. Technically, if that cliff wasn't there, you would be expending energy because gravity would be pulling you down. So anything that's above the Earth's surface, if it's just sitting there, it has the potential to have energy that is pulled by gravity. And for this one, we're going to use our gravitational potential energy equals ham. So h is your height, and that's measured in meters, again, so we can come up with our joules. Acceleration, that's due to gravity, measured in meters per second squared. Remember, on Earth, our acceleration due to gravity is 9.8 meters per second squared. Don't forget that number. And then our mass, which is measured in kilograms. So we're going to go through a couple examples here. How much gravitational potential energy does a 5 kilogram rock have if it is sitting on the ledge of a cliff that is 10 meters high? So we're looking for our potential energy. Our mass is 5 kilograms. Our acceleration is because of gravity. Notice it doesn't really say that anywhere except that it uses the word gravity in the problem. So our acceleration is 9.8 meters per second squared, and we are going from a height of 10 meters. So we're going to use our equation GPE equals ham and plug in our numbers. So we're going to have 10 times 9.8 times 5, and that's going to tell you that you have 490 joules of gravitational potential energy stored in that 5 kilogram rock that is 10 meters high. So let's go through these practice problems now. Be back in just a second. Okay, so a Viking ship roller coaster at the fair, like the ones that swing back and forth, has a mass of 36,000 kilograms. If at its peak it reaches a height of 20 meters off the ground, how much gravitational potential energy does it have? So we've got one of those fairground rides, and it looks like a Viking ship, and it just swings back and forth. So it's your lovely drawing of what's going on in this problem. Yay, everybody. Okay, so we have a mass of 36,000 kilograms, and we reach a height of 20 meters. And because we're off the ground, we have an acceleration due to gravity of 9.8 meters per second squared, and we're looking for what our gravitational potential energy is. So my equation is GPE equals ham, and I'm just going to fill in my numbers that I have. So we have 20 times 36,000 times 9.8. I did that out of order, sorry. It doesn't really matter, but 20 times 36,000. So this ride has a gravitational potential energy of 7,056,000 joules. For number 2, a 1.5 kilogram apple pie is sitting on the kitchen counter. If it has 13.44 joules of gravitational potential energy, how tall is the counter? So I'm going to write this off to the side because I don't have a ton of space. We have a mass of 1.5 kilograms, and we know that its GPE is 13.44 because it's just sitting there, it's not moving, it's waiting. We know that acceleration due to gravity is 9.8 meters per second squared, so we're looking for our height. So I have my equation of GPE equals ham, and I'm looking for my height. So because everything's multiplied, I can divide by everything that's not my height, which means I'm going to divide by my acceleration, my mass. So H equals GPE divided by AM. And then I'm going to plug in my numbers. So 13.44 divided by my 9.8 times my mass of 1.5. So let's see how tall this counter is. So this counter is 0.91 meters tall. Then we have a suitcase weighing 120 newtons. It's on a counter 1.3 meters high at the airport. How much energy does it have? So I'm looking for my gravitational potential energy. And I know that it is on a counter that is 1.8 meters high. Here's the tricky part though. It's telling me a suitcase weighs 120 newtons. So there's two things that I notice here. It's telling me weight and not mass, which is what I normally use. And it's telling me that it's in newtons, which I know is a force. So what this is already telling me is that my weight, my force, which is my mass times my acceleration, so my M times my A, so two parts of my ham, are already combined together into 120 newtons. And that's totally fine. They just did the work for us there. So I'm still going to use my equation. GPE equals ham. And then they've grouped my A and my M together for me. So I'm just going to plug all my numbers in. 1.8 times my 120 newtons. And that's going to give me 216 joules of energy. That one's a little bit trickier because we have to remember that weight and newtons are not just our mass. It's already the gravity times our mass. All right, so that's it for our first round of notes. You guys are going to watch a video tomorrow and then do practice problems on these that will be posted on Friday. So please just get these notes written down and submit a photo of them so that I can give you credit for it. All right, see you guys later.